we have the whole plane. Right? What else? Torus. Excellent. What else? Sphere. Right? In fact, the sphere is classic, is more classic than the torus. What else? Unions of torus, right? For example, the two torus, or the three torus. Here, this is a smooth, it's not a smooth. Right? Okay. So, you need house doors, you need second countable, and you need local ingredient.
Professor, is the union of open intervals also manifold?
The union of what?
Open intervals. One in case of one.
Yes, but it is not connected. Disjoint union, you mean?
Yes.
Like this?
Yes.
Yes, this is a manifold, but it is not connected, so we do not take into account just the connected components of the manifold. Yes, but this is also together with disjoint union of circles. Yeah. Okay. So we now have returned to topology using these metric spaces. I told you how to fabricate the topology in a field that has a cross valuation. And now what I want to tell you is the difference between the ultrametric inequality and the spaces that do not satisfy the ultrametric inequality. So we are going to explore just a little bit of topological phenomena in what happens in the ultrametric case, and then we will define what are called non-Archimedean fields, and I will discuss a little bit about that. Let's work a QP. So Q, together with the periodic valuation, is non-Archimedean. And I can consider the metric topology there. So I have a topological space. Now, let us consider the closed disk. Another way to say this is so in using valuations, I need to change this by this, sorry. I will explain why. But still, instead of using, so the problem is that if I want to use the maximal convention, I need to take power to transform additive into multiplicative. So the periodic valuation in multiplicative form is of the form P minus the periodic valuation of n. This is in order to transform addition into multiplication. But if I want to keep using just the valuation, I need to use the additive formalism. So this, believe me that this translates to this. So it's just different forms of taking the valuation. If you want to take the multiplicative one, you have to raise to the p minus power. And if you want to take just evaluation, then you have to use here 0. So this is a well-defined set. Inside for some p prime, this is a well-defined set. What I'm going to show you now is that this set, you know that this is closed, right? Because it is the closure of an open set. This is a ball. The basis for the metric topology for the topology induced by a distance are open balls. The closure of an open ball is closed by definition. I will show that this set is open. And if I show that this set is open, then the topology breaks down. The topology is going to be totally disconnected. It's what we call totally disconnected. So let me see if I can show that this guy is closed. So let me switch back to multiplicative and use the ultrametric inequality. And after this proof, we will take 10 minutes rest, 10 minutes break, okay? Because I think that this mathematics are very heavy for too long our course. So after this, we are going to take 10 minutes break. I want to show that this is open. What do I need to do? I need to pick any point here, and I need to fabricate an open ball such that the open ball is contained completely inside the set.
Yeah.
Let's take any point here.
So this set is open set, open as well as
Yes, yes. And we will show that any open set is closed, so the topology is totally disconnected.
Yes.
Okay, let me see if I can do it. So I take a point here. Let me take a radius which is smaller than 1. I will show that all the ball, do you prefer D or B?
These.
I will show that the ball centered in Y and with radius R is contained in the closed disk. Okay, so let me take a point here, and what I need is to compute the norm of Z, and I need to show that this norm is less, or here is 1, sorry, right? And let me take Z, and I need to show that the norm of Z is small or equal than 1. Right? So what I use is that the norm of Z to Y is bounded by R. Yeah, because this is in this ball. So the norm of Z equals the norm of Z plus Y minus Y, right? They all three. And then, well, first this, and then this. And then, by the ultrametric, this is less or equal than the maximum
Yes.
of the norm of Z and Y and the norm of Y. But this norm is R, is smaller than 1, and this norm is 1. So this maximum is, and I finished.
Yes.
This with an ultrametric inequality is closed and open. Hence, corollary, and this is before the rest. the break, corollary, every non-Archimedean field is totally disconnected. Is Hausdorff, but totally disconnected. This does not mean that the topological space is trivial. Trivial is with the trivial topology. It means that this looks like a Cantor set. Okay? So, let's meet back at in